out the way wire. Right, there's some things I want to discuss about the new. It's during the day, so the lights are turned off, but I'm hoping there's enough light. But there's something very interesting. Um, I want to explain about my new system, my new pulse driver circuit, and it's kind of interesting really because let me just see if I get my current meter for the output. It's a bit low at the moment because it's almost charged. I don't know if I can get this in there. It might not show up either because I don't know if it'll fit in. I mean, get it on the camera at the same time, you know what I mean? Oh, damn it. The angle's all wrong. I'm trying to... Let me just prop something underneath there a minute. I need something to prop underneath. That might work. I think that'll work. I don't know if it's going to fly out on me. I can't get my meter in. I'll stick it on the side maybe. It's going to fall on the floor if I'm not careful. I need to put a light on. Right, so that's the output current at the moment. It's low because the thing's just charged up now. It's about the relay just tripped now, so the current output is going up now. So it's charging at the current's going to go up as the loading. Now, what you'll notice very interestingly, this is how much power my device, my pulse motor generator is consuming, and it's very low. That's the voltage we're running at. We're running at 16.8 volts basically. That's what it's set to anyway. And interestingly, look at the current consumption on the actual device. It's only 260 milliamps. It's very low considering. It's very, very well. Now, there's something I wanted. Something came to me last night when I was trying to sleep, and it's about triggering modes of using the opto-isolators or timing to trigger the coil circuit, or using Hall effect devices versus coils. Now there's something very, very useful about sticking and using coils for the timing, because you see we're triggering a coil inductor that's pulsing the rotor assembly, and the timing is controlled by the actual inductance of the trigger coils. So we're actually driving an inductive load with trigger coils. Now it's beneficial to use coils rather than solid state opto coupling, triggering, because those are at the speed of light basically. There's no inductance involved, it's just static timing. But an inductive trigger actually reacts with the delay of the inductance in the way it charges up. So as the speed increases, we actually get an automatic leveling. It basically compensates by itself. Now this is where the current will show up now. Now look at the current on the input. It's actually 290, 280 milliamp, but it's slowed down a lot. We're only at, if you look at the meter across the room, which is over there, RPM. It's dropped down to 2,900 RPM right now, but the current on the input is only about 300 milliamps. It's current limited right there, but the output 125 milliamps now is going out into a 3.45 voltage load. So that into the supercapacitors. So supercapacitors are currently at 3.6 volts, and we've got 124 milliamps going out, and we're drawing about 300 milliamps to drive the device. And now that is extremely fascinating, because if I was driving my generator using an ordinary electric DC motor, my current consumption right now would be over 1.5 amps or something. It would be a lot higher than what we're seeing here. And I have been scratching my head a little bit about this, because I have got an extremely efficient timing now that I've got my timing sorted out. And the other thing that I found really interesting was how it seems to self-regulate, and the circuit itself, the timing circuit, it does appear to be self-regulating, because I've noticed that as the voltage on the output on the supercapacitors climbs up, because it goes up, it seems to, because of the way I've got my drag cancellation coil arrangement set up on my generator, the actual voltage and current output will actually increase incrementally in steps. It seems to go through this cycle, and to be honest, it was an accidental feature of my design. It was something that happened in my design by accident, which is very beneficial, because it means that at lower RPM I'm actually producing automatically governed current right up into the height until we get to the height, say 12-13 volts. But when we get to about 15-16 volts, the current output will drop right down to about 50 milliamps, which is what you expect, because my generator coils can't read the actual cyclic RMS doesn't get much above 15 volts anyway, so we don't really have much energy at that range, at that level. But now this next thing which I want to mention is what really surprised me. Normally I've got this double bank of batteries over there. Actually, I'll just grab them a minute. Right, so there's two sets of four. So there's basically two sets of 3S, but they're in pairs. So that's 4 sets of 3S batteries. Now, normally when I was running these, to run the motor that was driving my generator, pulse motor generator device, when I was previously running them, I wouldn't get more than about 2, maybe 2.5, 3 hours max. I wouldn't get more than, on a fully charged set of batteries, I wouldn't get more than about 3 hours of running time out of that. And yesterday I was running this, and I was a little bit surprised, because that thing, it's about this rating, it actually ran for about 8 hours. I thought 8 hours? I know that can't be right. That can't be right. I must be missing something. I must have got something wrong. No, I'm thinking, no, hang on a minute. Look, I started the thing at 4 o'clock in the morning, and it was still running at midday. So that's 6, 7, 8. That's 8 hours. And I was a little bit baffled, actually, and I was quite surprised. I mean, it actually ran for 8 hours. I thought, well, that's never happened before. I mean, previously on the other, when I was driving a DC motor, I got 3 hours, a maximum, and it would need recharging. I'll swap over to this other battery set down here, which is what I'm running on right now. And this is a pretty crap battery set. Normally with this thing, these batteries down here, they're just a bit of a mismatch of different batteries. That would normally run probably 30 minutes. I wouldn't get much more than 30 minutes to drive the system on the DC motor, a conventional DC motor, which is what I was using. So I was running this DC motor that you've probably seen in previous videos, and the bearing's not very good. I want to change the bearing out on it, put a new bearing on it and that, and this thing was consuming about an amp, a bit less, it depends on the speed, but running that thing, I wouldn't get more than 30 minutes on this battery set that I've just been showing you down there. But direct driving it using my pulse circuit, which I've designed, and the coils are wound, it's really doing well, and I'm happy. Sorry, I was just getting some. Right. So I'm really quite happy about that. I was surprised. You can see this, so it's got in the background the yellow trace is my output waveform. I need to get a good lock on it because it's jumping around a bit. Right, the yellow trace is the output waveform that's under load, and the blue trace is the coils that are in series that are doing the drag cancellation. I've got these little peaks on there, which are where the pulses happen, which I explained in previous videos. So I've got little pulses there, and at the bottom down there, which is basically where my drag cancellation pulses happen, which is, anyway, I don't want to go back into that because I've explained that in previous videos. But anyway, so the output at the moment is 92 milliamps. We're drawing about 350 milliamps peak, but it's fluctuating because it's a pulse circuit, and I've got a capacitor across these to smooth it out a bit so we can get a more average current, and it is pretty average that now, because I've got this great big capacitor at the back, which it's not a super capacitor, it's just an ordinary ancient capacitor, which is basically connected in parallel with the DC input from these batteries to the DC output of this unit, the actual unit that's sending the voltage out to my circuit board. It's across that to prevent spikes and pulses from upsetting the readings. So that seems to be working quite well. But anyway, to go back to the coil thing, using timing coils is a much better way of doing it, because the timing coils themselves are reactive in the way that the coil works, and we're driving in a reactive load as well, so it kind of compensates by itself. Whereas if we're using optical timing, or if we're using just a Hall effect device, because it's not actually a coil, it's just picking up a magnetic field, it doesn't have any reactive changes, it's a pretty static thing. Yeah, if I was using those particular timing things, I'd have to keep adjusting the timing all the time, but because I'm using coils to trigger the circuit, which you can see in my previous videos, you can see how I basically did that. It seems to work really well. My current really doesn't go much above 300 milliamps, even when I pump the voltage up, which is quite surprising. So if I take my voltage output, which is at 16.8, it's set up. Let's go up to 19. $19 volts output now. See, the current is pretty much the same. That's really quite amazing. It's gone up a little bit, but not much. we're at 4,102 RPM right now. So if you can read the meter, which is kind of my finger's too big, which is over there. Yeah, it's really quite interesting, is that? Yeah. So we're at 19 volts now, but I'll leave it at that anyway. It's doing really well. And we're pushing out 108 milliamps at the moment. It's on the meters on its side because I can't really get it all in, because I was trying to get the oscilloscope in, I was trying to get the current consumption in, I was trying to get the current out in one screen, in one shot really. Just ignore the YouTube videos that's in the background. I need to close that anyway. So it's getting warm. I don't know what that is. It's getting warm. It's getting warm. Oh, my coils, they tend to get quite warm. But check these batteries. These are all cold. These are slightly lukewarm. So these batteries are about to go flat on me. I'll take that back down to 17. What was it? 17.8 or something. Was it 16.8? 16.8. Back to 16.8. 300 milliamps. Yeah. So we don't see a huge difference in current consumption. We see a little bit of a difference, which you would expect. But it is much more efficient than it was before. I mean, if I was driving a motor directly, it would be using 3 times the amount of power than what it's using. I mean, 300 milliamps is really nothing at 16.8 volts. I mean, okay, my RPM isn't great right now. It's pretty low. That's because of the fact I'm running it on. I've got my drive coils that are actually in series right now. I really need to put them in parallel. But if I put them in parallel, the current would probably be higher. It'd probably be double what it is right now. So yeah, all I can say is that I would, if you're building something, it's better to use inductive trigger coils than because of the way that they actually seem to be. The rectangular coils are better. When I'm using the rectangular coils, like these ones are designed, because they actually produce a waveform that has a much bigger apex, a bit bigger peak, and it tends to be a lot narrower field, so it's got better timing aspects to it. I was going to draw it on a piece of paper, but yeah, you've seen the waveforms in my videos anyway previously. I think so. We're pretty much at 4,000 RPM already, and that's not bad. That's pretty good, really, considering the amount of current that's going in. So I don't know what else to say really at the moment, because I'm still half asleep really, because I only woke up a while ago and it's early morning right now, so I've only got my first cuppa. I need another coffee. Not the pair that's on the cup. No. Anyway, I'll put the phone up. So the circuit there, I still haven't built it. I made some more changes to my schematic because I realised I had incorporated some updates. So instead of 2 trimmers on each channel, I've just got one. I've got 2 trimmers, but one's for the balance between the 2 negative and positive pulses, and the other trimmer is for the gain. So I made some more changes to my arrangement for the schematic when I actually build it. And I decided actually, I was thinking the other day when I was looking at this, I keep making changes to this, I keep making improvements, so maybe I shouldn't build a circuit board yet, because I'm still it's still evolving, I'm still making little adjustments to it, and it's getting better as I do that. So let's not rush into building the circuit board right now, because otherwise I'm going to end up having to make another one. So I just thought, well, I'll leave that. So as you can see, no motor driving it, no belt. It's being driven directly by the two coils underneath, and it's really quite quiet at the moment. And so what else is there to talk about right now? I think that's it really. Just thinking aloud. Right. Anyway, I'll be back later sometime when I have some more news. Put my up right. I'm just thinking in case there's something I missed. Well, my time is optimal anyway. My timing is optimal on the unit. I don't think I can improve it better than what I've got it right now because of the way the current consumption is so low. Right, anyway, I'm going to go and grab some food. I'm hungry. Bye for now.